Research shows that more than 40% of users will abandon an application that takes longer than just 3 seconds to load. So while it may seem somewhat easy to design a performant application for a small number of users, to have that same application to perform well for millions of users can be quite a challenge. Today we're going to discuss how Flo Health leverages DynamoDB to achieve its predictable performance at the scale of 300 million users. My name is Lee Hannigan, and I'm a Senior Solutions Architect with DynamoDB. I'll be joined with Flo CTO, Roman Bogiev, and my wonderful colleague, Juhi Patil. Roman's going to kick off the session by providing you an introduction into Flo Health. This part aims to give you a foundational understanding of Flo's context and DynamoDB's role within it. And then if you've ever wondered how DynamoDB achieves its predictable performance, all while maintaining millions of requests per second, I'm going to take you through a DynamoDB deep dive that explains exactly that. In concluding our session, Juhi's going to lead a discussion on design and cost optimization strategies. And it's through Juhi's insights, we'll explore effective methodologies that allow you to decrease your DynamoDB costs, all while improving your performance. So I'm going to hand you off to Roman to take you through the first session.
Thank you, Lee.
Thanks, Roman.
Yeah, I'm very happy to be here on the stage to talk more about how we use DynamoDB to power our application. But before I will start, I want to ask audience, who knows the Flo app? Please raise a hand. Not a lot of hands, but it's not a surprise to me because our app is designed for women. And in audience, I see a lot of male engineers, which is understandable. And we are here to build a better future for female health. And we already achieved a lot. Right now, we have more than 300 million installs, 60 million of monthly active users, and 20% of US and also in UK, 20% of women use app like Flo on a daily basis. We helped 50 million of women to get pregnant, and this is just the beginning of our journey. I will explain a little bit our app because probably not a lot of users in this audience. So we have this foundational free features, which is cycle tracking or period tracking. This is a foundational feature. It's free of charge. Everyone uses it. It creates like a natural engagement into the app, and user opens the app like every month to enter the period data. Then we have symptoms tracking. We have anonymous mode for those who need like a special privacy protection. And it might be, in some countries, it might be LGBTQ community. In some other countries, it might be because of rules around abortions and so on. Health is a very big topic, and a lot of people experience this in a different way in different countries. So we need to be mindful about the privacy and data protection for those users. We also have a secret chat community. It's very similar to Quora or Reddit, but it's specifically designed to discuss health topics. And it's secret because nobody knows your name, so you can freely discuss topics like discharge, like miscarriage, and other important topics that you don't typically discuss in Facebook or Instagram. And then on top of that, we have a lot of premium features that are designed to help users to achieve certain goals or to manage certain conditions. So for example, we have a special content in the app designed to help users to monitor health issues, like for example, polycystic ovary syndrome or endometriosis. We have features to monitor and track pregnancy, a lot of different features designed for different users, but every user is different. Some are new moms, some tracking cycles, some want to get pregnant, some on contraception. And we can show all the features for different users to all the users. So we developed a special tool to manage personalization at scale. We call it user profile. And basically this user profile has a lot of data about user. Behavioral data, data entered by users through symptom tracking, different attributes like age, weight, BMI. Data from wearable devices is also stored there. It's one of the largest data sets about women's health in the world. It has more than 1 trillion data points. And this data is stored in DynamoDB. We believe that DynamoDB is a key to our success and to serve our users in the best possible way. On a logical level, you may see this architectural diagram. So basically, we have different data coming from machine learning algorithms, from manual input. We store data about commercial points, like lifetime value of the user. We store data about symptoms and so on in one central place. But it also means that this central place should be as highly available as possible, because if it's down, everything is down. So we rely a lot on high availability features of DynamoDB. Then we also created like a special tooling for our medical experts to build rules on top of that. So on one side you see tools that are used by our medical experts to build certain kind of rules. Like for example, here you see rule about ovulation and fertile window. And then based on these rules, we can show certain content, certain push notifications to end users. And we also can hide and show some features. And we can also personalize experience in a best possible way. We also use machine learning, but also medical rules, because we are in a sensitive and medical accuracy for us is very important. But what it means for the user? It means that every user will see different app. It will have like a different features. Some users will see tracker, some other users will see chatbots. Some users will see pregnancy mode, some other users will see content for teenagers, but some other will see for adults. So it's completely different experience for different users. And this experience is powered by DynamoDB. Here on the screen you see some statistics and some numbers and some features that we use to power this particular use case. We rely a lot on auto-scaling because we have a lot of users and they live in different countries, so we need to follow the sun in order to serve them properly. We rely a lot on high availability features. We rely a lot on things like encryption, because the data is super sensitive. And right now it's 1 terabyte of data just for user profile. And the biggest challenge that we faced with DynamoDB was the size of the one record. Currently it's limited to 400 kilobytes. So we need to be super careful with design of these records, because for every user we want to store as many attributes as possible, but it should be done in a way that will be sustainable, but also will be supported by the DynamoDB. But personalization is not just about features inside the app, it's not just about content inside the app. Communication timeline is also a very important thing to personalize. And some users wake up at 8 a.m., some other users wake up at 10 a.m. Every one is different. And also different features might be useful at different times. So for example, in the morning people log the symptoms, but in the evening they have more time for talking to chatbot or maybe reading content in community. So communication timeline is very important and it should be personalized as well. And then users have ability to customize the schedule. So for example, if they want to receive reminders about taking pill at 9 a.m., they will use special feature inside the app to get reminders at certain time. What it means for us that every user can customize the experience. But most of the users, they're not very creative with time. A lot of users put schedule on 9 a.m. exactly. So every day, every 9 a.m. we receive a lot of users who open the app because we send the push notifications to them. And the fun fact about 9 a.m. is that every hour is 9 a.m. in different countries. So it just it's non-stop 9 a.m. for us. And the biggest stress test for us when San Francisco wakes up, this is where we have the biggest load in our database, in our application. So in order to facilitate this communication, we've created special tooling. But before going deep into how this tooling works, I want to explain how communication timeline works. So we use the same rules as you've seen before, but we have like a time component for this rule. So for example, we can schedule a message to the user on 5th days of usage of the app. Or it might be on some other day, it might be a particular time, it might be scheduled for the morning or for the evening. And how it works, users open the app, we start logging time for this user, and then when time comes, we send the push notification. In order to manage this schedule, we use unconventional feature. we use DynamoDB TTL, which was designed to remove data from the database, but in our case, we use this as a scheduling tool. So we put a record into database to schedule notification, and when DynamoDB triggers deletion, we receive a Kinesis message that, oh, this message is scheduled for deletion, and we can send a push notification if it's time to send a push notifications. This is how it works on an architectural level. So everything starts from the user profile. So every time when user opens the app and logs some symptoms or maybe just installs the app, we populate user profile with fresh attributes. Then every update of the attributes creates like a message to the stream that, oh, this user changed something. Maybe it's like a new symptom. Maybe it's something else. Maybe they changed the goal of usage of the app. Then we process those messages to find like whether we have any notification which is relevant to this user. And if not, we put record into DynamoDB database to schedule something in the future. The trick here that in case of app itself, we have only 60 million of users who are active monthly. But with this pipeline, we have more than 300 million of users active every day. Why so? Because not everyone uses the app, but everyone can receive an email or push notification, and for that they don't need to open the app. So basically it means a lot of processing. And this is one of the reasons why we use a streaming architecture instead of batching, because basically here we can schedule on a user level, and basically for every user we maintain a different schedule. And for some users we can use some tricks. So maybe, you know, this user has a behavioral pattern and this user likes to receive like notifications. We can have like very dynamic schedule for this user. We can send like many notifications for these users. It may be on an hourly basis almost. But some other users, they don't like push notifications. Maybe they want to receive 1 notification per week. We can maintain like a separate, completely separate schedule for these users, and we can process them on a weekly basis. But every user is unique, and we use personalized schedule for every user. At some point of time, when we become successful and popular, we notice that TTL is not, well, we knew this from the day one actually. TTL is not designed for for such functionality because it has no SLA in a way that we need it. So for example, if you want to have like very precise schedule for the user, so for example, we want to send notification at 9 a.m. and maybe 5 minutes, it will be hard to achieve this with TTL if you have more than 50 million of records in your database. So in order to work with this challenge, we introduced like a new component which is called notification trigger, and basically it helps DynamoDB to process those TTLs, and it sits as a kind of like a backup, almost like tool for TTL. If TTL is not able to handle this notification trigger tool will trigger the TTL, and we will send a notification exactly when user needs it. A little bit statistics about this database. So again, the same auto-scaling is used, the same encryption, which is super important for us. Point-in-time recovery, with every database we have this. I think unique here is that we also use time to live a lot, and we rely a lot on this feature. Another unique thing here is that, as you see here, we have these spikes. Maybe our marketing team decided to send a lot of notifications. Maybe users scheduled some notifications at 9 a.m. in San Francisco. So we have a lot of spikes. And this is very unique challenge, but DynamoDB handles very well. And this is why we like it, and we use DynamoDB for this particular use case. I can't imagine any other technology behind the hood of such a tool. As you already know, we process a lot of health data. And this data is super sensitive. It might be data about pregnancy, about sex activity, about different symptoms. So we care a lot about data, and we store this data in the most protected way. We believe that users have full control of their data. We recently got double certified in security and privacy. We also have anonymous mode, which I already mentioned. And we recently got the Times Invention Award for this feature, because basically it means that like users can use our app without fear of being without any fears. And our PEI storage that stores all the personal identifiers like email, IP address, or IDFA, or any other technical identifiers that might identify user is also DynamoDB. And we use triple encryption here. We use a lot features like point-in-time restore and so on. I already mentioned all of them, but this encryption and reliability of DynamoDB is very important for us. And when we were certified by ISO auditor, we showed all these features and they were amazed how good we are at handling this type of data with DynamoDB. We are a very popular app already. Here on the map you see coverage or like adoption of the Flo in the world. And you see in the, at the top it's very good, like it's dark, but at the bottom it's not very dark, it's light. The reason behind this is our app is very popular in countries where people can afford premium, but in some other countries they don't have money to afford premium subscription with our service. But at the same time they need even more education about health and well-being. So we decided to make our app free of charge in 66 countries, including India, including some African countries, all the developing countries that need this health literacy the most. But for us, it means that like we need to handle more users and we need to handle them in a cost-effective way because it's free for them, but it's not free for us. So we rely a lot on DynamoDB in storing data in a cost-effective way. And my colleagues from Amazon will talk a lot about how to make it cost-effective. Because in our case, it's not just about sustainability or I know, money on a bank account. It's also whether we can afford 66 countries or 65, because every dollar counts. And at the end, I want to summarize my 6 years experience and our 6 years experience as a company with DynamoDB. We're very happy that we use this technology. We rely a lot on this technology, and we were able to build super powerful, super important tool for a lot of users with very small team of engineers. And we can handle scale as we grow. So I'm very happy to be here on stage and to present our experience with DynamoDB. And now I want to pass my microphone to Lee, who will talk more in details about how to build technology like Flo and how to implement it on a technical level. Thank you.
Thank you. Amazing introduction to Flo. Hands up who uses DynamoDB in production today. Whoa, good. Hands up who manages their own NoSQL database in production. Not as many. The complexity of handling your own distributed NoSQL database at scale is very complex. And that challenge is completely handled by DynamoDB as a service. That means that you no longer have to worry about managing infrastructure or becoming experts in distributed systems. All you need to do is learn DynamoDB's straightforward API in the programming language of your choice, and the rest is completely handled for you. DynamoDB offers predictable performance with response times measured in single-digit milliseconds. This means that your application can remain lightning fast no matter your workload size. This is done through DynamoDB's horizontally scaled architecture, which virtually means that there's no limit to your data or throughput needs. This ensures that your service can remain scalable even as your demand increases. DynamoDB is also secure and resilient by design. Your data is always encrypted at rest, ensuring robust protection for even your most sensitive information. Global replication ensures data availability across regions, and DynamoDB's 5 nines SLA and availability guarantees uninterrupted access to your data, even in the event of significant challenge. DynamoDB's serverless architecture is also very convenient and reliable. There's no more downtime, there's no maintenance windows, there's no patching, and you're always on the latest version. And with the pay-per-request pricing model, it means that you can wave goodbye to capacity management headaches, once again allowing you to focus on building applications without worrying about infrastructure. DynamoDB also seamlessly integrates with other AWS services, whether you're using AWS Lambda for flexible data processing, or other AWS services for machine learning or advanced analytics. DynamoDB empowers you to take full advantage of the rich AWS ecosystem, which allows you to focus on innovation. So I want to take you through a little bit deeper under the hood into how DynamoDB achieves its predictable performance, all while serving millions of requests per second. Before I can go there, I want to make sure that we're all on the same level. So the highest level of abstraction in DynamoDB is the table. All your data is just simply stored in a table. If you're coming from a relational world, similar to a database construct, inside the table, we've got items. And like Roman said, a maximum item size can be 400 kilobytes. But you'll see from what Juhi's talk will help you to design around that 400 kilobyte item size. Inside item, we have attributes. And again, if you're coming from the relational world, they can be similar to columns, but not quite. As you notice that DynamoDB is schemaless in nature, each item effectively holds its own schema definition in the form of key value pairs. We have a partition key. Partition key is the only mandatory key for your data. When you create a table, you must use a partition key. You must tell DynamoDB what your partition key is going to be and what type of data that's going to be, whether it's a string, a number, or a binary. We also have a sort key. A sort key doesn't only do what it says in the tin, which is sort your data. It's also really good for defining hierarchies and relationships in your data. Collectively, they're known as the primary key. The primary key defines uniqueness in your data. Each item must have a unique primary key. Then you'll see we've got these non-key attributes. And non-key attributes is effectively what makes up the rest of your data. So from this table here, we can simply say that, imagine attribute A1 is a user ID, and which is the use case for most of Flo's applications. Give me all the data for user 123, highly efficient, highly performant, single-digit milliseconds, great. But what happens for those use cases where now you want to read by email address? Just imagine attribute A5 as an email address, and I want to efficiently get all of the data for lee@amazon.com. That can be a struggle. For a small data set, you can get away with what we call a scan, one of our APIs that makes sure that you have to read every item in the table before returning a response. So small bit of data, perfect, but as your data increases over time, you'll see that your response times will decrease over time. Not only does your application become slower, but it also becomes more costly to make that same request. To overcome that, we have this solution called a global secondary index. And if you're coming from a relational world, you might kind of relate a global secondary index to a materialized view. You can define a brand new schema. You'll see one of our indexes here has attribute A5 as a partition key now, which happens to be an email address. So if I want to read lee@amazon.com, give me all of the information for that user, I can do so really efficiently by reading from my index. And now again, single-digit milliseconds, super fast, super efficient. Some things worth noting about a global secondary index. The first thing, I suppose, is that you can only have 20 per table. But if you want my recommendation, if you go beyond 10, then you probably need to revise your data model. Every second, unlike the DynamoDB table, where every item must be unique, items in your global secondary index do not need to be unique. And that's something that many customers overlook when they design their global secondary index. Global secondary indexes are also sparse in nature, which can help you reduce costs. That means that if you do not define the keys for your global secondary index in your item, that item is not projected into the index. So you could have 5 terabytes of data in your table, but you might have a sparse index that's only holding gigabytes. And one other thing about global secondary indexes is that you define the capacity for them separately to the table. If you're using on-demand mode, which we'll see in a little bit later, you don't need to worry about defining capacity. But if you're using provision capacity mode, you must provision capacity for your table and each of your indexes independently. Which takes me on to my next topic, capacity modes, provision versus on-demand. And what we're really trying to understand here is which should you use and why. But first I want to take you through how DynamoDB actually scales the data, how we scale it under the hood, and are there any limits? And if so, what are they? Then we'll take a look at capacity modes. Should you use provisioned or on-demand, and what's the reasoning behind each? So let's take a look at how we scale the data. Underneath the hood, I suppose, yeah, let's take a look a little bit deeper. So we're going to just go down the stack a little bit more. How we distribute your data under the hood is in the form of partitions. I'll take you through partitions a little bit more in a second, but for now the important thing to understand about a partition is that it can handle 10 gigabytes of data, can provide you 1,000 write capacity units and 3,000 read capacity units per second. So leveraging these partitions, we can horizontally scale your table in chunks of up to 10 gigabytes. And with this systematic approach, it allows us to scale seamlessly to millions of requests per second, as each independent partition is only serving a fraction of the overall workload. So what's the limit? And yes, somewhere up there, somewhere, there's a limit, but it's not worth thinking about. Essentially what you're asking me is, how many servers can Amazon shove into a data center? And the answer happens to be a lot. So let's go through now to see how we actually partition the data. Here we have a sample item. It's an order item, and it's got a partition key of order ID, order 123. On the right-hand side, we have your table, which is made up of many partitions. We have 3 partitions here, each one of them storing a specific segment of the entire key space. Then we've got an internal hash function. So we take your data, we pass your partition key to our hash function, and it outputs a hash key. I've abbreviated here just for simplicity, but we have a hash key of 7B. With that hash key, now we know where that physical item, or where that item should be stored on physical storage, and it ends up in partition B. Partition B is the one that's capable of handling that segment of the key space. So what's important to note about this is that any change to your partition key at all means a completely new random hash key. So the higher cardinality of your partition key, the more random distribution you get across your key space. And that follows NoSQL best practices. So how does the sort key come into play? Again, we have an order, but this time we're using customer ID as the partition key. So a customer has many orders. Customer ID 123 with order 000. With our hash function, nothing changes. We simply take the hash of the customer ID this time, which is 123. That ends up into partition B again. Second order comes along. Again, customer ID 123, order 001 this time. Do you think the sort key has any impact on the hash, or do we get the same hash? We end up with the same hash key, which tells us to go to that exact same partition, but this time you'll notice that the data is ordered by the sort key. That's the purpose of the sort key. DynamoDB stores data grouped by the partition key and stored on the disk in ascending order based on the sort key. So moving on, when should you use on-demand or provision mode, and why? So a lot of my time is dedicated on exactly this topic, talking with customers like Flo, trying to understand, should they use on-demand, should they use provision mode, when and why? But we first should probably start about where on-demand mode came from. So when we first launched DynamoDB, we mostly forced you to allocate provision capacity on all of your tables. And it sort of steered away from what DynamoDB aimed to achieve. We wanted to be fully managed serverless database. We wanted you to be able to select a table and just make requests to it. No need to be burdened by provisioning capacity or trying to figure out how much capacity you need. That's exactly why we built on-demand mode. You just pay per request. Create a table, make requests, let DynamoDB handle the rest. But the choice between on-demand and provision mode is, or should be, made on a case-by-case basis. And it's predominantly driven by cost. But that cost is not just about monetary costs. It's also about the cost of impact of throttling. So if I step back for a second and help you understand the impact of throttling on your application. Throttling occurs when you exceed your provision capacity for a sustained period of time. Essentially what happens is DynamoDB tells you to slow down. It's not a bad thing. You're just writing at a rate higher than you've provisioned. But how does that impact your end user? If you remember from the beginning, I said that 40% of users will abandon an application in just 3 seconds. AWS SDKs have built-in retries with exponential backoff. So every time your request gets rejected by DynamoDB, the exponentially backs off. Longer and longer and longer. Eventually you're tipping along to that 3-second mark where you're losing 40% of your users. You don't want that. That's detrimental to your user experience. So if you have an end user that's sitting there waiting on a request, either they're adding an item or getting an item, you want to be highly available and really, really fast. For that use case, the on-demand mode is perfect. But sometimes on-demand mode's not perfect. What happens if you have a downstream system that's limited in capacity? And we know that DynamoDB can handle millions of requests per second. So all of a sudden you're writing millions of requests per second. What happens to this service that's sitting downstream, listening to the changes, whether it's doing it from DynamoDB streams or Kinesis data streams? It becomes completely overloaded. So for some use cases, such as maybe ETL or bulk updates or something that you're doing that the user isn't sitting waiting on a response, throttling can be perfectly acceptable and probably almost wanted. So here we have an infograph, and essentially on the x-axis we have time, and on the y-axis we have the keys of your data. So essentially we're showing your data access over space and time. Hands up who has an application that looks like this. Didn't think so. Most applications look like this. Every now and again, you get a burst in traffic, and every now and again, you get a hotkey. So when customers come to us and they say, we know you want us to have this really nice, evenly distributed traffic, it's just not possible. Can you help us? And that's essentially why we built on-demand mode, to help you to handle unpredictable traffic. So when we launched DynamoDB, we only had provision mode, and at the time of launch, we had this blog post that had this infograph. Notice as the consumed capacity increases, application autoscaling also increased perfectly with it. Everything was smooth, really smooth. And on the other side, you see things decreasing. Everything worked great. So why do we need on-demand mode? Take a look at this example application. So we provisioned the capacity around about 7,500 WCU. On average, at the beginning at least, we were consuming around about 4,000 write capacity units. Then all of a sudden, traffic just spiked. Unpredictable, of course, as always. And then we handled that through a thing called burst capacity. And essentially, burst capacity allows you to exceed your provision capacity for up to 5 minutes. But in this instance, we see that we've exceeded our capacity for much more than 5 minutes, and that resulted in throttling. So what if we don't want throttling? So on-demand capacity was built in a direct relation to sentiments that customers shared with us. Customers said things like, our application is going to grow over time. Can you please help us? Or if you listen to Roman, San Francisco just goes through the roof at 9 a.m. every morning. But maybe it's 9 a.m., maybe it's 9:30. It's unpredictable because they give their users the power to choose when they want notifications. So customers like Flo reached out and says, can you please help us? This is the nature of our business. We can't change it. We can't smooth it. Our user experience is on the line. Do something about it. So that's really what on-demand mode does. For spikes that are up to 2 times your previous capacity, DynamoDB handles it instantly. No manual intervention needed from your side. But if you want to go beyond 2 times your previous peak, then there's a possibility that you may get throttled. And the reason I say possibility and not a guarantee is simply because underneath the hood, DynamoDB is always proactively scaling out your table without you even knowing. So there's no cost to us scaling out your table. We're actively monitoring. Usually if you're around about 50% of your throughput, we'll increase you more just to be sure that we can handle your spikes. And that means that you're fully available all the time. So we see a similar application to before. This table has seen 10,000 write capacity units in the past. So again, we're making around about 4,000, 5,000 write capacity units per second, and then a sudden spike. The spike's elevated for a long period of time, 18,000 write capacity units, much more than you were using on average. This time, it instantly scales. There's no scaling mechanism in the background, there's no lag. It instantly goes to 18,000 write capacity units per second without anything, no manual intervention from your side. You'll also notice then at the tail of the graph that the customer makes no more requests. At that point in time, they pay 0. Pay per request. DynamoDB scales to 0. You only pay for what you use. And the beauty about this is, the next time the customer has a spike, it can now go to 36,000 write capacity units per second, because your previous peak is now 18,000, and we promise you that we can do double your previous peak. So now I suppose the burning question, on-demand or provision mode, which to choose and why? If you want my nugget of knowledge, and something that I share with all of my customers, including Flo, is to start off with on-demand mode. On-demand mode is like tipping your toe into the water, trying to understand what sort of throughput you have. Is it really unpredictable? Should it go for on-demand that can handle unpredictable spikes in traffic, no problem? Or is it really smooth? It ramps up every morning at 9 a.m. and slowly back down at 6 p.m. Perfect for provision capacity mode. So start off with on-demand, feel it out, give it a few weeks, monitor your CloudWatch metrics, then you can understand. The long-term solution could be to change to provision capacity mode, which in turn will allow you to decrease your DynamoDB costs and will be a more long-term solution. And that takes me to our next topic, and I'd like to invite Juhi to the stage to take you through it. Thank you.
Hey everyone, thank you Lee. So Lee walked you through how DynamoDB works. Roman walked you through how Flo uses DynamoDB. Let's talk about costs. Let's look at how you can optimize your design and your cost. So writes are one of the parameters on which DynamoDB costs are calculated, and we'll look at a technique to optimize your write costs. Okay, there's going to be some math involved because we are talking about cost. There's going to be some numbers. So just stay with me for the next couple of slides, and then we'll go to the design technique. So what you need to understand from this slide is, for up to a write of 1 KB, you're going to use 1 WCU, or you're going to be charged for 1 write capacity unit, right? The next few bytes up to 2 KB, 2 WCUs, and so on. So then the question is, the limit is 400 KB. So how much do you consume for 400 KB? 400 WCU, right? Simple math till now. So now what are the trade-offs of having a big item? What are the trade-offs of having a 400 KB item? So the first one is, you're going to increase your read and write costs, because you're paying per read capacity unit, per write capacity unit, right? So bigger the item, bigger your costs. Second is going to be higher latency, because bigger the item, more the I/O cycles, more the amount of data you're passing through the network. So that's going to take more time to process. So the latency also depends on the item size. And thirdly, throttling. So say you make 3 requests of 400 KB each, and they are for the same partition key. So you instantly go over the 1000 WCU limit for the partition, and that could lead to potential capacity throttling issues, right? So now what is the actual, let's look at how DynamoDB works with updates to understand what's happening with this big update or a big write. So basically, say you're trying to update an item. What it first does is it's going to fetch the item from the engine, from memory, and then it's going to apply the update in memory. And then once the update has been applied, it's going to write it back to the engine, right? And because of this process, we'll see how your write costs are affected. So just to visualize it better, say you have this orders database and you're trying to update an item, right? This orders database stores all the line items in a single item. So that means, say you have an order where you placed an order for 10 items, for example. So all these 10 line items are present in the same DynamoDB item, right? So that's what this tells you. So for example, you want to change the status of your shipment, right? So that status update is going to be what? Like you want to change it from new to shipped. So that's going to be about 20 bytes if you want to change that string, right? But what's the size of your item? That's 20 KB because you're storing all your order lines in the single item, right? So what does it end up costing you? 20 WCU. Because it's going to apply the update in memory and write it back to the engine, it's going to cost you as much as the whole size of the item, right? But hey, I want it to cost 1 WCU because it's a 20 byte item, right? 20 byte update, right? So it should cost 1 WCU. So how do you optimize this? You optimize it by breaking your big item into smaller chunks of items. So this technique is called vertical partitioning, and Flo also used this technique to get over the 400 KB limit, right? So on what basis do you actually divide your items or break them down into smaller chunks? The first one could be logical division. So we were looking at the orders sample. So say you break down your order lines into one item each. So rather than storing 20 line items in a single item, you store them one after the other as 20 different items. That could be one way of doing it. The other one is static versus dynamic content or access frequency. So you have items that are read frequently but not updated frequently, while you have other items that are more static, so they don't change value at all. That could also be one way. So why touch those items unnecessarily, right? And one more way of doing or breaking down your large item could be by data integrity. So for example, any updates to your customer data, you might not want them to affect your orders data. So that could be one other way of bifurcating or breaking down your items. So again, visualizing it better, this technique of vertical partitioning, you can use it on the same order sample that we were looking at. And now you have two items here, one for each line item, right? The customer ID remains the same, it's customer 123, but if you look at the sort key, it now has your order ID plus the line item ID. So instead of one item with both those order lines, you have two items with one order line each. Now say you want to update the shipment for one of the line items to shipped, right? Now what you basically end up doing is just change that pending shipment to shipped. And now because it's just that one line or one small update that you changed, the item size, if you can guess, it's probably a few bytes, so it's going to be just a 1 WCU change rather than the whole 20 KB change now, because now you've broken it down into its own item, right? So it's more efficient. So if you want to look at the benefits in a nutshell, you have better costs, you have improved your costs, you have improved your latency, you have improved your scalability, and at the same time, you're also prone to better indexing with this design, because now your items are sorted outside of your array. You're able to index them as well. You're able to create global secondary indexes on this attribute. Right? So overall, it also allows you to have better distribution of data, and which can also lead to better fine-grained access control. So you can restrict your access based on line items as well now, right? So what are the trade-offs? Basically, if you look at, say you can imagine there's a 50 KB item and you want to break it down into a huge user history or like a chunk of user profile and then the line items. So say the big chunk takes you, say the line item takes you 1 WCU each or 1 KB each. So that's 1 KB of write for one line item, one more KB of write for the second line item, and then the big chunk of 49 KB or 48 KB, 49 KB, sorry, for the chunk, right? So overall, for the 50 KB item, because you broke it down into 500 bytes, and then 49 KB, you ended up paying 51 WCU instead of paying 50 WCU, right? But that's a one-time change. But if this application is update heavy, it's going to instantly give you a good performance, because then now you're just updating the 1 KB items rather than touching the static data every time and ending up paying those 49 extra WCUs every time, right? So that's the trade-off. If your application is update heavy, this technique is going to help you save on costs plus help you save on latency, all right? So that's what is this technique called vertical partitioning, and it's being used by Flo as well to overcome the 400 KB limit. So now, just to recap the session, Roman from Flo walked you through how Flo used DynamoDB, what Flo is. Lee walked you through how DynamoDB works under the hood, the horizontal scaling aspects, the capacity modes, and how to choose between the capacity modes. And finally, I walked you through a technique called vertical partitioning to have more efficient design and hence optimize your costs. So we have a few sessions which we suggest you could take a look, have a further read on. And all right, once that's done, you have Skill Builder, which is a platform for hands-on labs and free online courses. So you could actually redeem your 7-day trial if you'd like with the Skill Builder. And finally, thank you for your time with the session. I hope you enjoyed it.